FPGAs by Professor Kamalakant Mohapatra from NIT Rourkela. It's my pleasure to introduce him to all, as he is presently serving as Professor HAG in ECE department at NIT Rourkela. He assumed professor position since February 2004. His research interest includes embedded systems, digital VLSI design, hardware security, industrial electronics, and IoT. He has graduated 23 PhDs, completed 8 sponsored R&D projects, and has authored a huge number of publications. He received coveted J.C. Bose Award in the year 2014 for Best Engineering-Oriented Research. He is a senior member of IEEE and is currently serving as chairman of IEEE Rourkela subsection. Thank you. Now it's over to you, sir.
Thank you very much and for an introduction. I'll start with my topic. Am I audible clearly? Seti sir, just confirm me if I'm audible and visible as well as my slides.
Yes, sir. You are audible, visible, and your slide is also displayed. No problem.
Okay, thank you. So I'm going little off the line topic. Protecting IPs, IP cores, and then I'm saying implemented in either in ASICs or in FPGAs. Well, if you look at the title of your FDP, it is slightly different, but I deliberately chose this topic because this is what is the go of the day. I mean, this is what the thrust area of research, and since FTP is not essentially, is not exactly a keynote, it's kind of, you know, the majority of you would be actually practicing teachers or for that matter, PhD students and master students and so on. So we expect what are the research line where exactly the funding is available in our country as well as across the globe, so that people can actually take up research in addition to that projects, and so that they sustain in the market. But this is very much also falls into the topic in saying that whatever we call algorithms, see, algorithm, some people call it an algorithm, but when it is implemented, it's actually in the form of an architecture. We can't really do anything with the algorithm. Just writing a computer program doesn't help you anything. Ultimately, it has to go with a piece of hardware. And even if somebody says that he has to run that, he has to run it through some kind of hardware, whether it is a personal computer or PC or a DSP processor or a microcontroller or some kind of processing element. That is what is the issue. Now, what I said that there will be IP cores, means for every application there will be IP cores, and these are implemented either in ASICs or in FPGAs. I'm not very sure that what is the kind of background all the participants have, but I am going with an assumption that they at least know the basics of VLSI design. And even if you don't know, I'll again come back to you for knowing that what exactly is required. Yes.
No, sir, no problem. Continue, please.
Okay. So the whole philosophy here is that whatever we call it algorithms, that's ultimately targeted to some kind of architecture, that anything that you go and buy in the market. So it is in the form of some architecture. In the sense that if you remember what happened in the year 1998 in India, earlier to 1998, there are only two cars available. One was this Ambassador, which was Hindustan Automobile Company, which is now virtually extinct, except once in a while I find it in Kolkata and Mumbai, but otherwise I don't see it. Then there was another car called Premier Padmini. So that is from the Premier Automobiles, and then there was a Maruti 800. There are no other cars except some typical foreign cars with some typical people, but otherwise no. That particular year launched 4 vehicles. One was Hyundai Santro, one other was Matiz from Daewoo, Tata Indica, and then there was a car also launched from Maruti. They called it Zen. So these four cars, when they came to the market, that was the first time ever that they introduced, they say that there is a computer control inside the car, which means that earlier to that 1998, whatever cars we had, whether it is Ambassador or Premier Padmini or Maruti 800, they didn't have a computer inside it. And in reality, what these cars had is that they had either 8-bit or 12-bit or 16-bit microcontrollers inside it, and they were trying to control something. And that control was actually, those years, there was a Euro 2 compliance came up that the pollution is going very high in India, and that's because the emission is not really controlled. And in order to control the emission, they said that this has to be maintained by the car companies. And how do they manage it? So in order to manage that, they say that if the air fuel mixture in the right combination goes in, then things would happen. So for that, they wrote down computer programs, they wrote down algorithms, but how do they implement inside a car? Now imagine that car is a sort of device which runs on the road, signals has to go in, signals has to come out, so that there is a valve through which the air and the right amount of fuel would get in. Right amount, as you know that you are driving in first gear, second gear or top gear, or if you are driving an automatic vehicle, then you say that there is no gear, but it's automatically driven. So the right amount of fuel would actually get in. But who would decide that? That decision would be done through some kind of algorithm. And that would be decided on various factors: what speed you are running, what is the tire condition, what is the road condition, and where exactly you are trying to drive. So when it is done, so then the right amount of fuel comes, and that right amount of fuel that is coming over there was actually facilitating maximum fuel efficiency. That is one part, but indirectly it was also facilitating that the pollution was getting controlled. And pollution getting controlled was the dictation by the government of India. And therefore, in 1998, whatever all the forecasts launched, they introduced this micro. And that year, uh, uh, if you had looked at the advertisement, which is already 24 years old, they said that we are going with these microcontrollers, microprocessors, that we are going with these microcontrollers, microprocessors, computer control, and all these big words. And all these big words said that we are doing some kind of algorithms over there, and that is being converted to kind of architecture. Now that architecture, whether we say it is in the form of an ASIC or in the form of an FPGA, those years, of course, they used all microcontrollers. Similarly, I'll give you one more example before proceeding further. If you look at the washing machines in the Indian market, it's almost 2 years prior to this car incident, 1996, a company called Samsung, which is world's largest semiconductor unit, I mean, number one in the consumer electronics, they came up with saying that their washing machine is neuro fuzzy controller based washing machine. And people suddenly started being confused. What is big deal about neuro fuzzy controller based washing machine, and whether we should buy that or we should not buy that and all that. But people again got tempted, and people were advised, since it is from Samsung, when they're claiming is neuro fuzzy controller based washing machine, this must be something very wonderful. Okay. And then the market of Samsung was catching up, and the only company who tried to counter it was LG. LG those days was also known as LG, which we call as life is good. That is what their advertisement goes on. But it's basically Lucky Gold Star company. And Lucky is a chemical company, Gold Star is an electronics company. They joined hand and they became LG, whatever it is. LG is also a very well-known brand today. And those days, they also came out to counter this. So they did an entire reverse engineering on the washing machine supported by, supplied by the Samsung. They purchased it, they broke it, and they tried to find it out. And then they found out that there is a typical IC which is doing something. Now, if you look what exactly a washing machine does, because nowadays almost everybody uses a washing machine, you know that there are several parameters. The amount of load that you put inside the washing machine, what is the temperature of the water, what is the type of clothes, in the sense that whether it's bed sheets or silk or cotton or whatever, and what is the amount of that level and all that. But at the end of the day, what the washing machine does, it says that it is rotating a motor and for a specific amount of time. So what Samsung actually did, that it ran an algorithm, which is of course based on neuro-fuzzy controller. It was offline, entirely offline. They ran that particular algorithm, and they tried to find it out that what would be the best condition if this is the data level, this is the load level, and amount of load 5 kilo, 7 kilo, or whatever, and this is the type of clothing, cotton, whatever, and then the result is that this must run for 37 minutes and the speed is this much. And they found out this one using a neuro-fuzzy controller. Now, but if this algorithm has to run, where it would run, and how this result has to come in. So they say that you have to go in with an architecture. But they really didn't do any architecture. They have taken a lookup table just like any of your FPGAs. And in the FPGA lookup table, there are 6 inputs from the washing perspective, and the two outputs says, and they've stored the whole thing in the form of a lookup table. Now, when LG could realize, because they did a reverse engineering, they also came up with another, the same soft computing technique, which was another soft computing, which they called it Chaos Punch. And this was also released in the market. And then there was a stiff competition between
बसिक रूम पढ़ हॉस्टेल के मुझे अलाउ नहीं पड़े मुझे हैनो ना पढ़िबो हला
any specific.
Yes, sir, continue.
So they did a reverse engineering, and the reverse engineering satisfied that it should be Chaos Punch. And so they came up with a washing machine. And that washing machine is also launched. And thereafter, now the next Seti sir, either you ask the participant to switch off their, I don't know, microphone is off.
Repeatedly mute. Yes, sir, continue.
No, if you are webinar mode, then all the mics will be off.
Yes, sir. Dear participant, please mute your mic. Dilip Kumari, sir. Please mute your mic.
Whenever we ask them that any questions, it can be unmuted, but otherwise, there is disturbance and there is echo as well. Anyway, it's fine. So we'll go ahead. So now all that I wanted to say that yes, they were using an algorithm which was neuro-fuzzy controller based algorithm, or LG used an algorithm which was Chaos Punch algorithm. But both these algorithms were translated into an architecture. The architecture has to be implemented either through an ASIC or through an FPGA. Okay. So we go to the next one. Next one, I'm just saying that it is ASIC design flow. Okay. Where I'm saying that we start with the design specification. Design specifications will actually come from the requirements. Then you will go for the specs. And from there, we write down the SDL codes, RTL description. Once upon a time, the BSDL was popular, and then nowadays, more or less, it is very long. And then we say that the functional verification has to be done. And then beyond functional verification, in the sense that RTL is fine and the functional verification is correct so that your IC is doing good job. Then we go for logic synthesis. And once we do that, then we say that gate level netlist. The reason for going for the gate level netlist, because if you are going by front end design and then we are saying that gate level is the lowest level that you can get into. And after that, we make the corresponding checks. And once that part is done, then we go for the PR and the place and route. And then we go for the physical layout. After we do that, then we do again another verification, which we call it the physical verification, and then finally GDS. So the graphical display, interactive interaction, that part has to be done. And once that is done, then we are done with our ICs. And then, of course, if everything is going on fine, then we will send it to a fab lab. Unfortunately, in our country, we have only single fab lab at Chandigarh. And specific fab labs at DRDO lab and ISRO, no ISRO. ITI, that Indian Telephone Industries ITI at Bengaluru. And the one that is most famous is the one that we are having at Chandigarh Semiconductor Complex Limited. Earlier it was under ISRO, right now it is under MAIT, Ministry of Communication and Information Technology. Now, anyway, now here I have skipped few things because my assumption is that people understand ASIC design. So either you are going for custom design or semi-custom design. When I say custom design, everything has to go from the scratch. I mean, you have to start with the transistors and then going up and up and up. Now, the whole philosophy here is that if I'm doing an analog design, then I can believe that I'll go with this one. But if I go with, digital design where the numbers are heavy, means say 20 years back we had Pentium 4, where 44 millions of transistors were there. Today we have i5, i7, i9 and that kind of processors where 3.5 to 4 billions of transistors are there. And today we are using iPhone 12 and similar kind of devices and similar phones also. That was iPhone. Then we have that iPhone is from Apple. Then we have MediaTek processors and Snapdragon processors, which are used either as Android phones or similar. They have 11.8 to 12 billions of transistors. If you have a digital design which have that many number of transistors, then there is a real problem that how do we manage this? So you can't really go with a customized design. So we go with the semi-custom design. So the previous one, whatever I said here, is more or less the semi-custom design. The kind of ICs that we had designed in our labs in NIT Rourkela, the first ever IC that we designed here was also a very simple design. Simple, I say that because many people, we used only 3 to 4 millions of transistors. And that was meant exclusively for anti-lock braking and collision avoidance system for a vehicle. And it was implemented on a CAN protocol, controller area network protocol. So so if you look at that kind of design, that also said, I said it's a simpler design. It has got only 26 number of finite state machines. But even then, we had lots of issues for designing it. It took us 4 years. My whole team took 4 years to do this. Maybe we are not too experienced at that particular stage. And in a more recent time, when we designed something for a chip for energy harvesting system for an IoT application, we took again almost 2 years. So the cost, even if it is semi-custom design. So that way, what I mean to say that yes, there are challenges. If you go for custom design, if it is an analog design, and you go for custom design, if you are exclusively, you can afford that much time and afford that much money, because custom design is way expensive. So that is the reason custom design is avoided and people go for semi-custom design, particularly when you are talking about digital and mixed signal designs. And the other approach is that, and please note that whenever we are doing this IC design, we never try to compete with Intel. I mean, you can compete with Intel i7 or i9, never. Because if you are going for a design, then it will take you 4 to 5 years, and by the time you go with this one, Intel will come up with another processor. This has happened historically from 8088 till today. 8088 they went with 80286, 386, 486, Pentium, Pentium 1, 2, 3, 4, then Itanium, then all these I's, and now at i9. So what we can really design is some of the embedded processors. Embedded processors means they are meant for specific jobs. Jobs like in a washing machine, there is an IC. Your TV has got an IC. All your gadgets has an IC. And similarly, there are many other applications. And I'm not saying that only this kind of consumer electronics, but also your many of the typical DSP imaging algorithms that you have got a digital camera, what kind of algorithm you want to put in over there, and then yes, it has got an IC. If you are not really interested in ASIC design, that many people say that we want to go for a FPGA design flow. The steps that we follow, I have written down over here: design entry, followed by the synthesis, then we implement, and we generate the bitstream files and upload to the board. And if you look at that on the blue color, I have written that after the design entry, I have done a behavioral simulation. And then the synthesis part is there. We are conducting functional verification. We say that my whole job is fine. And then we do a static timing analysis. And in-circuit verification is done only after uploading to the board. And the same thing, I'm just putting it, how exactly it is being done in a particular Xilinx stuff. So that is, anyway, I'm not showing anything different. Translate, map, place and route. And this translate, map, place and route and all these things I'm saying, just like many of you could be a signal processing specialist, as the name suggests, for the FDP. So there are, you could always complain that you are a VLSI engineer, so that is why you are good with that. So there are other scenarios like if you are a signal processing engineer, you don't know much about VLSI. Yes, MATLAB codes can be translated and then it can be done. But remember, this is what I wanted to tell you. Look at the code and look at the circuit. This code again is SDL, but this SDL code can also be generated from MATLAB, which most of the signal processing people, when they write the algorithms, they do it in your MATLAB only. Okay, and but the VLSI people, they say that we don't bother about the MATLAB anymore. We straight away go with SDL code. But if it is not available, you have to do it like this. So that provision is there not only from MATLAB but also from SDL and like VHDL or Verilog. It's, you can convert C, you can do it with system C, you can do it with Python, everything. So that is what is talked about. But at the end of the day, it is a circuit or an architecture. But anyway, that's fine. And now I'm talking that what exactly in VLSI design we try. And this is what I have mentioned in my abstract that I have submitted. If you have gone through that, so the first thing is that the VLSI uses certain design metrics. And what is a design metric? In the sense that we are objectively evaluating a design. So the design metrics can be used to compare and evaluate products, but and the different concepts for what? The maturity of the design, that we are trying to do something, and then on the basis of that, because we are saying that this is the design matrix, if it is masked, then we'll say yes, it's a good design. If it is not masked, then we'll say it's a bad design. Okay. So for example, if I say that I have got my mobile phone, and my mobile phone, the photograph quality should be this, and how to do this, that the designer has to do it, and then I say that it must last its battery for this many days. What is its power dissipation, whether it matches or not. And if it is becoming complicated, let us say for understanding specs, But engineers easily understand this. And you say that everywhere there is a spec. The one of the simplest example, I would say that every one of us uses AquaGuard. This is of course from one company, but then you are using some kind of water purifier. Then there is a spec. The spec says that in 1 minute, 1 liter of water comes out. That's what is the exact spec of a AquaGuard installed in the home. In the hospital, airports, and hostels, whatever we put in the industrial grade, in 1 minute, 3 liters. If it matches, yes. So we have to say that there is some specs and this has to be matched. But what are those metrics we have to define? And that is what I wrote in the last line. Designer, it is important that he specializes in the design metrics. That whatever he wants to do with the robust design. Okay. So for doing that, I said in the abstract, we are using PPA. That is what is the number one, performance. The fourth one, power. The fifth one, area. And there are two more terms I have introduced now, because this is what we actually look at in the VLSI design. People say that, are you so much concerned about the speed? The answer is yes. Because if you look at the specs of your i7, i9, then people say that it is operating at 3.8 gigahertz. And there are many such similar scenarios. Your mobile phones, the computation has to be done, and so many things. The speed is very, very important. People say that they cannot wait for the latency to be done over there. Now you say that there is a World Cup and the match is being done there, but there should not be a delay in this match. So they are recording over there, then they are transmitting. You are watching over a TV. You cannot wait for a delay. So the speed is very, very important in the sense that you are taking a photograph, then the imaging analysis and the clarity has to be done. It has to be transmitted through cloud, and then you get it on your TV, and you want that there is no delay. So that is why speed is important. But one serious constraint is the speed and power. They are two things. They don't go hand by hand. Whenever we increase the speed, the power also increases. Okay. Actually, power dissipation is P. If you look at the standard expression, P equal to CV square F. And this, of course, is nothing new. All of us have known a standard formula that energy equal to half CV square. When we have read in our school days, energy stored in a capacitor half CV square, and that is energy. If easy to difficult, then you can say that as kilowatt hour, the energy meters installed at our home, and then you are dividing by hour, that becomes, so that is why you are dividing by time. So that is why the frequency is coming in the term. So that is why I said that power equal to CV square F. And if you say CV square F with increase in the frequency, remember that power is also increasing. So therefore, don't be very crazy about speed unless otherwise it is not required. If you think that yes, it is a required, it's in RF domain, you require a high-speed transmission, you require some radio waves to be done, something really speed required, then you go for this one. Otherwise, there will be a serious power consumption that would happen. So that is why, and here, when people in VLSI engineering did this power for the low power design, there are a lot of criticism coming up that why this low power design is required. The low power design is not new. It's almost 30 years now. In 1992, we had the first ever research paper coming from Berkeley, and now it is 30 years, which means that first research paper coming in IEEE transactions, which means that you can add up another 3 years, almost 32 to 33 years. Now, but still, then people said that why these guys are doing this low power design, they're making so much noise about that. What is so great about this? But people should realize that, don't you think that we are charging our mobile phone almost every day? It's not that it is allowing me a week even or a month. I have to charge my cell phone almost every day because you know that. So it is dissipating power, and your battery has a limited power, so it can be done. And then you talk about your laptops. You run it for a few hours, it again goes. But then when you give such examples for the portable devices, there are many other people who say that this mobile phone, laptop were not there once upon a time. You are still surviving. What is so big deal about that? But then we always try to give them a more serious examples. More serious examples where power dissipation is an issue. I'll give you a serious example, then you will realize what is so important about power in VLSI design. So we know there is a device which we call as the pacemaker. And when I say it's a pacemaker, it's not a replacement of heart, but it is a device placed inside the human body, and that facilitates better working of the heart. Okay, and nowadays placing a pacemaker is not a very tough design. It's a design which is actually being done in almost all medical colleges. So now imagine that there is a patient who requires a pacemaker that's being done, and he comes to the hospital. The surgery is carried out, pacemaker is placed inside, and it is successful. Now he goes home. Now suppose after 3 days you declare that no, it is not working anymore because the battery is exhausted. And now what would you do on earth? Now imagine that, can you bring that patient again to the hospital and then again conduct the surgery and replace the battery? Which is next to impossible. That's simply not possible. So you can't afford to do that. So whenever we are putting that pacemaker, we expect that the pacemaker would run at least for 10 years. And this 10 years is not just a magic number. And why 10 years? People would always complain that why not 11 years? Why not 9 years? Well, that 10 years has been some kind of specs people said. And we have deliberated when we have designed on this VLSI with medical doctors. So the doctors, what they say and whatever they have asked us, we have been able to do it accordingly. They say that pacemaker usually in a young man does not require except rare cases, but usually it is installed at the age of 55, 60, 65 or so on, and let it go for 10 years. And after 10 years, if the battery is exhausted, because there was a serious constraint that yes, will your battery still survive beyond 10 years? That was becoming tough. So they gave us a challenge. We said that 10 years, and the 10 years is being met. And then he will probably come to the hospital again and another 10 years. So if you say now, the fast pacemaker was installed in 62, then he's going up to 82. And hopefully the person won't survive beyond 82 or so. But nowadays, if life expectancy goes, he'll go to the hospital for a third time. But you can't ask him to go to hospital every day. So this is one example I said. The similar example which I would tell is an hearing aid. Hearing aid are of two kinds. One which we put it right over here, this is external, but there are hearing aids which is put inside the kennel. And you can't every day take it out and every day put it inside. And the whatever battery that you put inside that particular hearing aid, that should last for at least a year or 2 years or so on. And that is why the low power design is required. This was, of course, done in our labs. In fact, my first PhD student developed a hearing aid which was inside, supposed to be put inside the kennel of the ear. So when you did it, we said that the challenge is to make it a low power design so that it lasts for at least a couple of years, 2 years or so. Because this is not that complicated as a pacemaker surgery. So if we say these examples, then outsiders would appreciate that yes, these engineers are doing something. They're doing something for the humanity. And I'll give you one more example that there was an accident in our country which we call as the tsunami. Now, in order to protect tsunami, nowadays we put sensors inside the deep ocean, and then we collect information from that. And when you try to put the sensor inside the deep ocean and try to collect, which means that we are actually developing an system on chip, and that was there, and that has to be again low power consuming. I can't send a person every day to the deep sea and then say that the battery is over. So that's not possible and feasible. So these are the issues which says that yes, low power design is very, very important, and at least for all the gadgets which are portable and some of the critical devices used for healthcare and used for similar scenarios. Okay, but now I added up two more parameters which I said which are not included. Another one was cost and reliability. Why I say cost? Because whatever you manufacture, this has to come at a very competitive cost. Otherwise, you will not sustain in the market. You just imagine that why in the India has not got its own TVs, own electronic gadgets, own washing machines, own in the sense that is totally indigenous I'm talking about. See, if we look at the TV market, you look at LG, you look at Samsung, you look at Sony, you go to the washing machine market, you again look at, LG, again Samsung. So there are so many. Of course, in there is IFB and there are few others. Siemens is again another German company. So look at all the gadgets, and then you are finding that, and the mobile phone again the biggest. Is there a single Indian company mobile phone? There was something called Carbon. It didn't last for a longer while, and we are still dependent on Apple. We are still dependent on typical Android phones like Xiaomi, OnePlus, and so on and so forth. So why it is not happening? Simply because we don't have a fab lab in our country, and we are not fabricating our own ICs to be installed inside the gadgets. Right now, our country is taking certain steps. Whatever we are hearing from Modi ji and our communication ministry, Ashwini ji and all that, and they are claiming and they are giving us some hope that yes, something would come up in the semiconductor manufacturing. Okay, and if that is true, then of course the game will change. We will probably have our own stuffs. Now, when I'm talking about the cost, I'm telling you a very realistic fact. See, some 12 years back, I designed my first IC in my lab. And when I designed, typically when I tried to do it, I looked at the market, and then I had to fabricate in Austria Microsystem in Vienna, and it cost me around those days. It cost me around 4,000 euros, which was typically 3 lakhs in the INR. Okay, and they provided me 20 numbers of ICs after fabrication, with a declaration taken from me that I will exclusively use it for my research, because when the IC was meant, it was said that anti-lock braking and collision avoidance system to be installed in some kind of automatic vehicles, maybe inside a car. And remember, in still those days, we never had a car with anti-lock braking facilities. Today, of course, a lot of cars on Indian market, like your Hyundai, Honda, Volkswagen, and so many of them have anti-lock braking. In 2010, none of them had. And when we did this, but that Austria Microsystem clearly got us written that you can't use it for any of the commercial applications, and we didn't use it. So that was, as I said, that I'm just trying to give you the cost of an IC. I said it was 3 lakhs. And if I had not declared that, they would have increased my cost at least 20 times, which would have come to 60 lakhs. Now, question is that 60 lakhs is not very important. But imagine that if I design an IC for 60 lakhs and I install in my car hardly cost me 5 to 10 lakhs or 15 lakhs. Then will this ever survive in the market? Now, the question is, if you make 1 lakh cars, then after the first ship is done, then the next 1 lakh, they will say that just the material cost you add it up, your research cost, your everything is done. So if for the next 1 lakh, I have to pay 10 lakhs. So 10 lakhs plus 60 lakhs, 70 lakhs, and divided by 1 lakh is 70 rupees INR. So if I got my IC done for 70 rupees, then yes, I can put inside my car and my car will function well and I'll be buying. But the question at that point of time that will I be able to sell 1 lakh number of cars? If I don't sell 1 lakh number of cars, then what is the point of fabricating 1 lakh number of ICs? There is no point. Okay, so that is what the car companies cannot guarantee. So this is what is the exact problem that is happening. We don't have our own fab labs, and the fab labs we are dependent on elsewhere. And now, when we are dependent on elsewhere, the cost is becoming rocket high, and now the everything is gone up. And then there is another thing is that unless otherwise we don't fabricate in that kind of numbers, then it is not a problem. But fabricating in that kind of numbers should not be an issue, as you know, that every sixth person on earth is an Indian. With every sixth person on earth, because we claim about 140 crores of people in our country, and you know how many mobile phones are required. Then why can't we have our one? Why can't we have 1 lakh mobile phone from an Indian company being manufactured? So these are the issues that is happening. So therefore the cost remains an issue, but the cost must be very, very competitive. And if you cannot compete with the cost, you realize that you will not survive in the market. And that is the reason we have not been survived. But hopefully a good time is coming, and the reliability is again another important thing. And the reliability and this particular one, this security, this is being added up. Now, this security, of course, stand of its own. I'll get into security in detail. That is what is meant for this particular lecture, IP protection. That for every IC that we manufacture, those days we are calling it IC, nowadays we call it system on chip, because we are actually manufacturing whatever is for a system. Okay, and that is why we call it it's a system on chip, and that needs security. Well, I'll just give you one simple example, and then you can realize why it is important. Today, wherever medical facilities are not there, then people say that using IoT, you can be treated. Imagine there is a patient at IGS Rourkela. IGS means Ispat General Hospital. Rourkela being a steel city, it has that kind of hospital. But there is no famous cardiologist over here. And his treatment has to be done by a doctor, a famous cardiologist at Apollo Hyderabad or AIMS Delhi or some similar kind of stuff. Okay. Now, his ECG is being taken and in real time it is being transmitted. I'm trying to say that what is importance about security. Now, when you are sending this information over the internet, there is an age notes and every point. And what we expect that whatever image that has been captured over here has to be exactly transmitted to the other end, to the doctor. Okay. And if the doctor sees, then yes, he says that where is the difficulty, where is the peak. There are different things. I'm not elaborating those things. Then he will suggest medicine or surgery or whatever. That should be taken care of. Now imagine that there is some hacking or some kind of intervention when the data was transmitted from IGS to Apollo Hyderabad. Now the doctor, there was an image which was captured. It is being sent continuously. And now it is going to the doctor. Doctor is saying at Apollo sitting over there, he's saying some abnormality and he suggests something. Then the IGS doctor says that, what is this? Is this doctor is a specialist or is a crazy man? What kind of security is doing? I mean, what kind of prescription? I'm not a great doctor, but at least my average knowledge says that this should be done. And why this has happened? Because you are sending this information and this information is getting tampered. It's not only over I deliberately gave this particular example because if I give this example, people say that yes, there is an importance of security. But otherwise, if you give so many examples, we'll come to that, and therefore we'll look at what is IP protection and similar kind of things. And then people realize that yes, there is a need of security. So far in VLSI design, people only said PPA, power, performance means speed, A means area, but nowadays they are saying security. I'm not talking too much on area because gradually over the years, we have been able to scale down our devices. Today, we have 4 nanometer devices that's in the market. We designed our Pentium 4 way back with 130 nanometer technology. And so area is being automatically taken care of. But remember again that there is a issue about the density in the sense that the two most designs which are very popular in digital, one is processor, another is memory. So whenever I talked about the processor, as I said that you don't compete with Intel, but talking about all other kinds of embedded, like starting from copy vending machine to your whatever small thing, or your digital camera where it is talking about the image processing algorithms and similar one, or whatever, your mobile phone, everywhere, we said that it has to be designed. So we said performance, power, area, PPA. Now we say security. Two other terms, I'm just assuming that that is implicit. Functionality is the first thing, that whenever I'm designing an IC, it must function correctly. If it is a simple IC like 7474, which we have designed in TTL, which is a D flip-flop, you say that how a D flip-flop would work, and then you would say that it is working correctly, and then the IC is fine. But we are not talking about those things. We are saying that yes. And then talking about the reliability, this will also fall under security, and we'll look into that. So on the basis of this, as I said, security, this security becomes a serious constraint. Security stands of its own. There are two kinds of security. One is hardware security, another is software security. But whenever we talk about the IoT edge nodes, imagine that there are millions and billions of devices connected, and we are into that kind of things. And the edge nodes, the software security becomes kind of vulnerable, whereas the hardware security would be a more serious challenge. And with IoT coming into picture, the hardware security gives even more. It has become even more serious a challenge. So we'll take up that a little bit on IoT, and then I'll get into security. So this is of course a standard picture. You must have seen it many times, and I have copied it from comsec.org. So all that it says that there are lots of connected devices, and the connected devices, if you look at vehicles, like there is an aeroplane, there is a car, there is a truck, there is all sorts of other kinds of devices also. And then there are other kinds of gadgets, and there is home, and then you will talk about hospitals, you will talk about our social, like dustbins and similar kind of things, then a lot of things. So they are being connected. And this is the standard definition of IoT. And the first one is based on Wikipedia. So interconnection of uniquely identifiable embedded computing like devices. So this is what is more important, that what kind of devices you are trying to connect. I'm not trying to connect some book or some physical things. I'm said that it's embedded computing like devices within the existing internet infrastructure. And IoT is expected to offer advanced connectivity of devices and systems and services. One is M2M, and M2M I'm talking about the fact that particularly when we're talking about the industry, because the industry doesn't want to go to a sleepover mode for more than an hour. There was a time when a particular machine is down and the industry was still not very happy. They were expecting, particularly I've seen in Rourkela steel plant, say 30 years back when I'm a young man in this particular campus. A machine is down, yes, fine. They called engineers from Germany, comes here, does it 7. But today, if anything happens, it has to be done in few hours. Otherwise, the whole thing goes down. So because you are competing with other steel companies. So anyway, that's fine. So we said the interconnection of these embedded devices, including smart objects. So smart objects in the sense that most of us are using, like Fitbits. I'll show you what are those. Is expected to usher in automation in all fits. And we'll talk about advanced applications like a smart grid. And this is the same stuffs again I'm repeating over here. We said devices, vehicles, buildings, and other items. And whenever we are doing this, what exactly we have? We have electronic devices. Then there are sensors which actually sense and get information. And then there is connectivity and internet protocols. And then there is software. And all these things are done to collect and exchange data. And then some typical examples that we use in IoT or otherwise, Amazon Echo or Google Home. So this device is very much there. I mean, typically we call it Alexa. So you ask Alexa to do anything, Alexa will do it for you, whether your train is running late or you want to listen to a Mohammed Rafi song or whatever. And wearables like Fitbit, then you want this information to be sent. That's again, I've deliberately given some of the very common examples that whatever we are doing it. And then this third one, I have written it as our country is demanding that we want smart cities. Smart cities. I just added up smart cities, smart villages, smart country, and smart region. Just not look at smart cities. Everything we want to be smart. And I have given an example, Barcelona, and the Barcelona, most of us are well known terminology, but this was the first ever smart city that was really developed. And what is they did, I'll come to that. And then we're talking about this connected cars. And this was first developed by AT&T Bell. And then, of course, smart grids. And this is very important a concept nowadays, smart grid. And these are the various applications, nothing new about this, but I again deliberately put hospital example, then people realize its importance. Otherwise, people say that these electronics engineers are only making an iOS for us. Anyway, we'll take because it's almost 55 minutes, we'll take a 5 minutes break and then we'll come back.
Okay, sir.
Okay, sir. I'll be back in 5 minutes. Professor Sethi, I think we should resume now. Is it fair enough?
Yes, sir. All the participants are here.
Okay. So I'm just putting on this IoT market. So as of 2022, 20 billion of IoT units across the globe. And this is continuously growing. And 70 billion IoT devices by 2025. So, I mean, another 2.5 to 3 years. Revenue growth, you can look at this. And side by side, let me tell you that something that happened in the last few days. USA government is going to spend $50 billion on the security. And the Indian government has also declared a similar figure, and India is going to spend 30 billion USD. That's the equivalent kind of INR. I just said 50 and 30 because that's what is the ratio in which India is trying to spend for the security. And why they are concerned about the security? The reason they are concerned about the security, if we cannot make our devices, whatever is connected, secured, then there is no point in going ahead. So that is the reason. And imagine that when US government and Indian government both are concerned, so also the other government. So other figures I'm not trying to put in. But these two, if I say, then you say that this is what is going to happen. And this is, of course, the same old stuffs. But you can look at the typical examples like power chips, built-in sensors, firefighters, etc., etc. Now the question is that whenever I am making so much noise about security, why be concerned about IoT? Because the IoT is the reason which is further compounding the security issues. All these same issues we have with access control, vulnerability management, patching, monitoring, etc. And now, whenever we are saying that, if I say that this is a million number of devices connected in a specific network, and any compromised device is a foothold on the network. Any compromised device, because if you have got a single device which is compromised, then the whole thing is going to be corrupted, and you are going to lose your data, and there are going to be lots of issues. And what are the issues that's going to happen? We'll discuss and deliberate. So now the question that comes, that does IoT add additional risks? See, first point I have written, are highly portable devices captured during vulnerability scans? The answer is yes, because you are trying to look at, and this, if it is, what is your network perimeter? Because in that particular perimeter, your device is there, somebody is trying to catch you up. Are consumer devices like healthcare where reliability is critical? The answer is again yes. Reliability is very, very critical in healthcare. Do users install device management software on other computers? So this can also be an attack vector. So if you now look at threat versus opportunity, the first 4 points I just wrote down from there. These are the additional risks. And I just made it over again, saying that these are the stories that's likely to happen. And therefore, if misunderstood and misconsidered, IoT poses risk. Risk to what? Our data, our privacy, our safety, everything. See, somebody took my data away, then my privacy is gone. And not only that privacy is gone, sometimes the situation is catastrophic. If understood and secured, IoT will enhance everything. So that is what enhance everything in the sense that communication, lifestyle, and services, and so on and so forth. And when I said it is catastrophic, there is not only that I said your healthcare is one issue, and there are many, many examples that you can always think of. Particularly, you look at an airplane landing, and if the data is not properly envisaged, or there is an attack, and then you find that the pilot is trying to come down, and then he doesn't find a way how to land. Okay, the runway is not there. And because it's a misinterpretation of the data, he thought that yes, the runway is free, he can land, and then he will do the taxi and reach to the terminal. But that's what is not happening now. Now, then what happens? At this stage, he cannot do anything, and then the whole thing is gone. That's again catastrophic. Similarly, I say the fire extinguisher. Fire has broken out at a specific space, and then you know that the information is going. But if the information is misread, instead of going to the location X, fire brigade goes to location of Y. So then there is no point. So what it says that we need to be absolutely cautious, and that is why the governments are also becoming cautious. And then you would say that then forget IoT. But if I say forget IoT, then that's not an answer. We have to live every time that we have come up with anything better as regards to the technology. There have been challenges, and when there are challenges, we have come across. You just imagine that when we said that at some point of time, we said that there is virus in the computer. And if there are viruses, then we have come up with antivirus. We have tried to protect. And nowadays, you might have realized, see, if you look some 15 years or 16, 20 years back, the virus was serious. But nowadays, you don't have that much. OS has improved like anything. So also the other factors, so that it's not so much risk. So similarly, now there are two choices. You say that there is no IoT. But imagine that if there is no IoT, then I am not talking to you. Because of the IoT, I am being able to talk to you, and my gadgets, devices are connected over here, and Professor Sati is recording, and the participants are listening, and so on and so. And we could still counter Corona during those days, work from home and everything. The world didn't stop. It might have slowed down a bit, but that's because of the IoT. So you can't say that leave it. So we have to live with IoT, and when you live with IoT, there is a security issue. But now the issue is that we must take care of that. So that therefore now the question is that hardware security I'm talking about. I will focus more on to the hardware security, because software security is, I won't say simple, it's a parallel subject, but hardware security is something that is becoming greater challenge. And this money that I said about USA and India is all on this hardware and hardware security. So there is a lot of opportunity for engineers who are taking up hardwares in the next few years, at least for the next 1 decade. There will be a lot of jobs, a lot of job opportunities, and the similar kind of research, and the people can always ask money to the government and all kinds of agencies, because when government has expressed its interest, and then obviously you can imagine that this is going to happen. Okay. Okay. Somehow I'm just trying to put some of the examples where you will say that if I say these examples, you will say that yes, there is security. Healthcare, I said ECG waveform being sent. If I say digital camera, you said what is photograph and what I have to do. But if I say ECG waveform, yes, it's a DSP algorithm trying to optimize everything, and then you are trying to say. Vehicular, if I'm saying that the vehicular is being used for crime assistance, then yes, it is fine that you will say that yes, IoT is important. And agriculture, if I say smart irrigation, then you will say that yes, fine. Now pollution, if I say identify the proper vehicle which is doing that, and industrial, identify right machine which is defective so that you require a correction. So we said security and hardware security, but why that issue is coming is primarily because of this globalization. This is what I would like to say, effect of globalization. And remember that what is globalization? Globalization in the sense that depends on contract manufacturers. I said in the beginning that we don't have a fab lab. So they in our country except SCM, Semiconductor Complex Limited. So we are dependent on whom? We are dependent on TSMC, Global Foundries. There are many, TSMC, the Taiwan one, Austria Microsystem. There are many of these fab labs. So we are dependent on them to manufacture the chips. And the second part is that when the chip is being manufactured, the testing has to be done. And in order to do the testing, we are dependent on OSAT, assembly, packaging, and test. So that is again outsourced. It's not of our in-house. And dependence on third-party IPs. This is where I'm talking about the intellectual properties, core vendors. Now, the whole point is that you would say that why not you design yourself? I said that in digital, it is next to impossible that I will design everything of my own. As I said, if you say that I am going to design a mobile chip, there are 12 billions of transistors. Can you imagine that how exactly you are going to write down the architecture, how exactly you are going to translate? So this is not feasible a solution. So in digital design, most of the time, what we do and what most designers on earth do again is that they are dependent on third-party IPs. And you would say that what are the third-party IPs? So for example, if I say processor, you all of us realize that the processor means there is an ALU, there is a MAC unit. MAC unit is more prominent in DSP processor. In an FPGA, you have a DSP processor and similar. And in a typical processor or a microcontroller or similar, you have registers, you have memories, you have such kind of things. And you will realize another thing that in the digital design, many of the designs are actually repetitive. If you have got one memory cell, there is so much of memory cell which is again repetitive. So there is no point in it. But the point is whether I want to use my own design or I am to depend on others. In most cases, we depend on the third-party IPs. That is what I'm saying, the intellectual property. Now, these third-party IPs will be available to you at both copyleft as well as copyright permission. When it is copyright, you pay money and get that. When it is copyleft, it is already available freely. Source code is available. You take it, you do your own, and then you do it. And then core vendors in the application domain. That means a particular company has developed a specific IP, he has kept it. You may reuse it for something else or some of your applications. Then you pay them a money and get it. Okay. But there is a third issue that I said is the service providers or consultants being involved in a design, like all these processes, verification, post-silicon validation, pre-silicon, everywhere. So there are essentially three things. One, we say that digital design, or for that matter, mixed signal design, is too complex. We don't design the whole thing ourselves. We are dependent on IPs available elsewhere. Okay, it doesn't matter whether it's copyleft or copyright, but we are dependent on them. And if I say that I have to do it myself, yes, you do, but it takes so much of time that you can't sustain in the market. Okay, so you are dependent on them. Then the other part, I said that a lot of service providers are there in the market who are known as consultants, and they are available at all places. They can do design for you, they can do verification, they can do testing, they can do post-silicon. And also we said that yes, there is contract manufacturers. That's of course our deficiency, but and OSAT. Okay. Now, when this is happening, what is the reaction? These changes of fragmentation of SoC design across the geographies. It's not at one place. And then I said, because I said in the beginning that I'm going to talk on this IP protection. Third-party IP core vendors, contract manufacturer and service providers located in different countries. Not only that, they are placed in, I said that my fabrication is done in Austria. Maybe I hire a consultant from somewhere, maybe say Portugal. So now the whole thing is that this fragmented business model in both design process as well as semiconductor supply chain raise several hardware security issues. And this, even if you have everyone from the country, just imagine, I'll give you a simple example that imagine that today I'm working in TI. Tomorrow I resign from TI, Texas Instruments. I become a consultant. But because I have worked for a long time with TI, I know already certain things that is there. And then I can leak their design to some other place, or I make a malfunctioning in their design and keep it as a copyleft permission. And tomorrow some other company uses it, and then he gets into a soup. He can't do anything because it has taken years for completing the design. So now the question is that what exactly is the solution? Now these are the stuffs that is coming over here. The first one is counterfeiting and overbuilding of chips. You want to protect, but try to protect it. We said counterfeiting. Counterfeiting can be many types. One is overbuilding, and the other one is aging process. Anyway, I'll come to that. IP violations. IP violations means it was given with a copyleft permission. I took it. I made some deliberate modification or inserted a Trojan inside it. Trojan means some few lines of program. When you will translate into an architecture, it will go wrong absolutely. Or I insert a time bomb. Time bomb is exactly like the time bomb that we talk about as you watch in movies and similar scenarios. This doesn't activate immediately, but it activates after a certain time. So such things are there in your ICs, and now just imagine that you have got a TV and in which your IC is there. IC works absolutely fine, but there is a time bomb as regards to this IC design. So what happens is after working for 30 days, on the 31st day, suddenly the TV starts malfunctioning. You can't watch anything. Now what happens? The company gets a blame that the Samsung TV is bad. The next one I said the hardware Trojans. This is another kind of hardware security issues through which we need to have our protection. Then we talk about test and debug security, because testing is very important parameter in the semiconductor supply chain. So we have to talk about this test and debug security. And then we talk about the different side channel attacks. This side channel attack is not only that, never think that this is out and out a software topic. No, it's not a software topic. It is on an IC, and there are different kinds of analysis that's done on an IC to check it. The sensitive assets of the SoC. That is what I have clearly said. Different side channel attacks on the cryptographic cores and sensitive assets on the SoC. It is not. So now I specifically categorically put what are the side channel attacks. Power analysis. So you have got an IC and you do a power analysis, and if the it's unique, then it will show the unique results. But if there is a change, the second one is the DFT or test infrastructure based side channel attack. Timing analysis again, and fault attack. And then there is possibility of doing it electromagnetic ledger based side channel attack. And multi-level attack means combine timing and power, timing and electromagnetic, timing and other kinds of things. And this counterfeiting, this is what I said. Counterfeiting is a component, the discrepancy in the performance, in the characteristic, but sold as a genuine chip. And why it is happening? Because recycled parts from the obsolete electronic equipment. This is one reason that's something we are trying to recycle. We are again reusing it. Unlicensed and overproduced parts coming out from the foundry. Okay. Out of spec or defective part means every company, when it designs, then it says that before it sends to the market, the testing is done, that it is correct 90-95%. So no issues. It's sent to the market, but immediately you realize that there's something is wrong. And that is what is. Now this overprice, this is not only that it happens over here, you can just imagine, and if I'm saying this is for an IC, many people again get a confusion that is it a real story. But just imagine that Dr. Reddy's lab, you hear that's a very famous company in our country, and they manufacture some medicine through some manufacturer. And imagine they are ordered for 1 million units. And the manufacturer, instead of manufacturing 1 million units, let's say that it manufactured 2 million units. And it supplied 1 million units to Reddy's lab. The other 1 million unit, they supplied to other supplier. And they say that, okay, now here you only provide us the material cost and our profit and sale. So this guy goes to the market, it's a similar one. The cover is changed and the whole thing is gone. This is an overproduced part. Now, who is the loser? The origin is the loser. Dr. Reddy's lab, if you say the origin, now they are the loser. The same thing does happen over here when you say that the unlicensed or overproduced parts are coming out from the foundry. I asked, just imagine that I asked a company, Austria Microsystem, that you use this and fabricate and give me my ICs. They gave me 20 numbers of ICs and charge me 4,000 euros. Just imagine the same company, Austria Microsystem, supplies 1 million of, I don't say that they have done it or anything of that kind. Imagine a typical scenario. Now they supplied, let's say 1 million number of ICs to Hyundai for no cost except for the cost of the company. The cost of the material. Now, what it says that if my IC works absolutely well for until of braking, this is a safety feature in your cars, it's a safety feature in your bus, everywhere. Then Hyundai gets this for no cost. So there, where is the losing part of the game starts. So that is why I gave you a medicine example saying that the moment you talk about unlicensed or the overproduced products, then you have no way of controlling it. And similarly, we say that the defective parts coming of the outsourced test counters, that when the testing is done, just like every company, whenever the final product goes to the market, they make a thorough test before sending it. But sometimes they clear it, 99% correct, send it to the market, let us see. Now, whatever is thrown out, that thrown out parts, if again sent, then there is no way that it can survive. That is why it is said that it is difficult to mitigate the recycled parts from the obsolete equipments entering the supply chain. However, what we can do, the detection techniques and trusted source of supply are the possible solutions. Okay. It is possible to develop techniques to mitigate that. So we have to do it. Now here is, of course, a huge taxonomy that I'm putting it. What are the possibility of the counterfeits? We said recycle, when we said that the aging is there. The same thing you can again talk about that the company produced some medicine and it is already aged, but I still produced changing date of expiry, something different. So the original company gets a bad name. Then we said tampered, backdoor and silicon time bomb. As I said that the IC works nicely for 30 days or 40 days as the time bomb sets. Now, what is time bomb? A particular code written into that and the architecture being set already. Clone. Clone means if I can produce a clone, that is actually done through the reverse engineering. And I can overproduce, of course, I have already talked. Defective, something defective, and again being said about that. And if these are the possible counterfeits, what are the detection methods? We said that there are aging fingerprints, means if I do a path delay analysis in the using the IC, that will tell me what is the age of the IC. So accordingly, I can find out that this is an aged IC or the right kind of new IC. Early failure rate, if you can check for a particular set, then you can identify. Similarly, it can be done using electrical inspection. There are tests burn-in test, functional test, parametric test, and physical inspection is also possible, particularly ACM, scanning electron microscopy, and other kinds of X-ray imaging, and so on and so forth. And this is, of course, I'm talking about again the IP course, and that is being available. I said that across the globe, it's not at the single place. If you look at these are the areas when I'm talking about mostly USA, and then some portions in the Europe we are talking about. Then India, we are exclusively focusing on to Bengaluru. And then, of course, there are areas like TSMC, Taiwan, Singapore, that kind of countries. And there are three types of IPs. One is soft IP, which is SDL code, a farm IP, which is in between, hard IP, which is the physical design layout. This, of course, I'll tell you that what kind of IP we should use. Now, here I'm talking about the hard IP and soft IP. If you look at the structure, hardcore, we say that predefined organization. Softcore is purely behavioral source code, technology independent. So technology independent means you have just written a code. It can be used for any technology. But here, when I said predefined means it's already defined. Modeling as a library component, it's already there. And here we say that softcore is synthesizable. And when you talk about the flexibility, this can be changed by anybody. But here you say that it cannot be designed by this one. It's already done. You can't do anything. And here the timing closure is defined, is not guaranteed. And softcore means weak and source code are available. But here we say it is much stronger, usually corresponds to a layout. And the correspondingly for FPGA, we will find it FPGA bit stream that is available in my first, second, third, fourth slides. And here's GDSII for the IC layer. But here we say VHDL very long. So what it indirectly I want to conclude here that hard cores are better. Okay. But then hard cores are better in the sense that you would say that, but there are limitations as regards to hardcore. As you know that there are certain things which cannot be changed, and here nothing can be done. Protection, of course, is strong, but then here there are certain issues. But if we can ensure that these are free from the security issues, then probably we can go ahead. So now coming to the IP protection techniques, this we said that passive and active techniques. Passive technique, we said the watermarking, widely discussed passive technique that is there from long time back, and people have said it, and most of us are familiar with that. In many of our image processing algorithms where we do it, and the same thing we do it when we translate into architectures, and then we say that some the timing and the power signature. These techniques are useful to identify IP violations and litigations. And active techniques, only the right kind of user will be able to do it. Functionality is unlocked when appropriate keys are applied. Otherwise, you cannot unlock its functionality. So therefore, it's like any of the software, hardware dongles you are using. So similarly, you can say that you can only use it only if you have that key. Otherwise, you can't open your IP at all. So the genuine customers will be provided the key. Everybody won't be provided that particular key. And there is an issue because every IP needs an evaluation. That because there are many of the ICs, if you say, then you realize that it needs an evaluation. So IP vendors allow potential customers to evaluate their functionality and specs. The evaluation period is limited. That is why they say that you can't say that you can't copy, and specialized keys should be designed to log the IP after the evaluation. I mean, if they have given you, you cannot say that I'll copy it and then I'll use it. So they will lock it. Now, here we talk about the hardware trojans. And hardware Trojans means you should be thinking that what exactly is this? See, what exactly is this? If someone says you say that, okay, you write down some programs and that is getting translated into some types of architecture and it is becoming a part in the IC. And who is doing it? You will say that who is doing this, putting this Trojan? I designed my IC. You designed your IC, but as I said that there are many other players other than you. You designed your IC in your lab. You said that I wanted a wonderful digital camera in my mobile phone. Absolutely fine. You have done that. But you are not doing everything. Your IPs are from somewhere. Your consultant is someone else. Your fabrication is elsewhere. Your testing is elsewhere. So if somebody is able to do that, insert that particular one, then you are gone. So that is what is said. Rogue elements can insert malicious circuits into design. So that is what is said. Circuits. I said that it's both way possible. Algorithms, you change the codes, and when you translate, it becomes circuits. Trojans can control, modify, disable, and it even goes to the denial of service. And you would say that what is its intention? So the intention when the virus was there in the software, that time also the intention was a similar kind of thing. You wanted to damage my reputation, you want to do this. So there are competitors in the market. So if somebody wants to damage your reputation, then you will do it. Absolutely. So hardware Trojans can be inserted during design phase. That is in the pre-silicon because you are trying to do it. GDSIA is way more protected, but it's not absolutely protected. And in foundry, because the foundry it is going there, you are not fabricating, someone else is fabricating for you. And he has GDSIA, he inserts something else. So that is why I just said that where are these? There are insertion phases, abstraction level, effect, and then this. Insertion phase, whether it is at the specification level, design, or during fab, or during testing, or during assembly. So what is that it is affecting? It is affecting everything, system to physical. Activation mechanism, there are different, always on or triggered, and triggering can be done internally or externally. Internally, time-based, as I said, time bomb. And externally, with some other user input, you put some input which you will be required to put at some point or other. That you have to do. And the effects are, these are the effects. One is change of functionality, that you wanted something, something else happens. Degrade the performance, leak information. This is the most dangerous things, and particularly for the space and the defense organizations. If it leaks information, your ICs, and then everything is gone. And you wanted to locate your enemy plane, something else happens, and you just cannot control anything. At that point of time, the defense of the whole country is at stake. And where it is located, location can be anywhere again in the piece of hardware. It can be at processor, it can be at memory, it can be at IOs. These are all ICs. Power supply again. This is again an IC. Don't say that power supply is just a power supply. Again, because you know that your SMPS is a piece of hardware, and that is again using another IC or the clock grid. And physical characteristics, it will try to do changes everywhere. So now the next one is that pre-silicon hardware Trojan insertion points. Who can do it and at what particular level? So if we are talking about IPs, then just imagine that the third party IP or 3PIP we say, RTL level yes, gate level yes, layout design also yes. And if I'm saying that again IC protection, then I'm talking about in-house IP development. RTL softcore, yes. You are developing an IC, but you have someone consultant and then whole thing is gone. So this you can look it through, and these are the different places that we can actually look into. Now the question comes that can we detect hardware trojans? The answer is yes. There are pre-silicon techniques, there are post-silicon techniques. The only thing or the only counter question you may ask me at this point of time that if there are detection technique, why worry so much? Why worry so much is primarily because whatever we try to design, see, there were all these issues were coming up for the last 20 years or so. People have been actively conducting research, so also the industry in the last 10 to 12 years, but it has not matured. So every day something new problem is coming up and we have to counter it. Okay. And if you want to counter it, then how do we counter it is the issue. So pre-silicon techniques, the functional verification, this is of course a standard technique, but it is said that it is difficult, needs special stimulus. Manufacturing test patterns, FPGA simulations, and then hardware Trojan detection techniques using static timing analysis. This is possible whenever we are doing this STA part. And then, of course, the formal verification. This is, of course, is a more powerful technique compared to functional verification. And post-silicon technique, again, we say that test pattern to trigger rare possibilities on a T and bench characterize. And side channel analysis hardware techniques. Hardware Trojan attack models and detection possibilities. I have given some 6 different models, and there are different stops that is being shown over there. The first one is important for us because we said that we want to protect untrusted third PIP vendor. So he would say that this is untrusted. Then SoC developer could be trusted, foundry could be trusted. So this is possible. This is one model where this is possible. When I'm saying that untrusted foundry, I'm just putting that this is untrusted. And if this is untrusted, what are the possibilities? Post-silicon detection? Yes, difficult. Untrusted EDA tool, you would say that how can you go for untrusted EDA tools? See, the question is that the EDA tools we buy from the market, from Silicon, Synopsys, Cadence, Mentor, other things. But there are a lot of tools also available otherwise with copyleft permissions. How can you guarantee it? Unless otherwise you start from small designs, you develop a faith, and it's not that the university guys like me and you are doing it. It is mostly some of the rogue elements who are doing it because it is available with a copyleft permission. They try to tamper it. And here now I'm saying this is the costs, commercial of the cells. Whatever you think that here everything is untrusted, so you can have a look into it. So anyway, it's a similar kind of thing, so there is nothing much. And hardware Trojan defense, there is a good possibility that hardware Trojan will go undetected in both pre-silicon as well as post-silicon. So on-field defense is important. And today, these are the current research that is happening. Hardware Trojan defense is based on the following: DRM keys and security during booting, access control, flow tracking, everywhere we are trying to do. And in the test and debug security, this is important because we are also dependent on the OSAT. In the current SoC design, corner issues. There are a lot of corner issues that you have looked like, particularly clock domain and the cross power drops and so on. So that part has to be very clearly defined that what exactly you should get it. And if there is a mismatch, then you can always identify that yes, there is a problem. The recent advancement in the post-silicon debugging are able to find out highly sophisticated errors and bugs. And regular assertion checkers to monitor malfunction. Silicon odometers, which will actually take about the aging component, just like the odometers that you put in your vehicle. And access to these instruments in non-safe environments, because these SOCs are part of some of the instruments that we have to look at. And the solutions, cryptographic techniques in everywhere, test and debug facilities, because this we are also dependent on. This POP is a solution where we are trying to protect the counterfeiting, that is overbuilding and IP protection. POF means that expansion is already given, physical unclonable functions. And here we talk about primarily challenge response time. I mean, why this is important? Because this is one of the solutions for many of the techniques and also for the IP protection. And here what we say that we add an extra circuitry where we say that this POPs, this we are saying that strong POP and weak POP. Strong POPs means more challenge response pair and weak POPs means lesser number. And you would say that what is that POP? Yes, it is another addition of a circuit. Or in your algorithm to architecture, you would say that you have added few lines in the algorithms that has been translated. And the POPs can be many different kinds. Like it can be an SRAM POP, it can be a ring oscillator POP, it can be an arbiter POP. And and here we evaluate a POP using uniqueness, uniformity, and reliability. And these are the three stops that I'm putting it. And you can make the check. So your original circuit itself is already changed. But that's a protective element which will try to protect your device. And here we say that IoT is a device security. That is, all these are possible scenarios in attacks in the IoT scenarios. Node capture and malicious code injection, that somebody does it deliberately, side channel attacks, sleep deprivation, denial of service, the most serious one, hardware software exploitation. On this particular area, I have done a lot of jobs, particularly age security. But in this particular presentation, I'm not putting too many stuffs over there. But whatever we are trying to push in is basically we are saying that with IoT, the security has become even more serious. When IoT was not there, security issues were there, but with IoT, the security issues are more serious, primarily because you are connected into the internet and everything are coming there. So these are the different possibilities that is over there. So now my conclusions, industry and academia has recognized the problems in hardware security are serious and working towards finding solutions to these problems. Okay. And as I said, up late, government also has become serious because government is finding that it's going to stop. Just imagine that certain things stop. You just cannot work tomorrow. So that is what I said. Security has become another tenet other than power, performance, and area. So that is what I said, timing, power, and area. In the next few years, security awareness in every step of chip design flow will become mandatory, especially in spec, design, verification, test, and physical design. The solution to hardware security problems will directly or indirectly address the problems in the edge security devices. These are some of the references. I haven't given my references. Maybe I'll add it when I'll share my PPT with Professor Setti or Professor Hutta or Professor Mahati, whoever is there. I'll send it tomorrow, and when I'll do that, I'll add my own references, because we have been working as a team in the last 10 years or so, and we looked at that particular tenet, security other than power, performance, and area. Now, some of the common things that I would love to say here, that whenever you would say that you are doing VLSI design, you will say that what exactly that I'm trying to do. And when you are saying that algorithm to architecture, this has become a little bit older word, algorithm to architecture. because people said that this DSP algorithms or image processing algorithms, and it has been translated to architectures. Yes, it has been done. And what exactly you have to do? People would say that, are you talking about area? I would say that area is no more a concern because your entire design has already been transferred to a lower technology. So you don't worry about that. Okay, just imagine what is the size of your mobile phone and accordingly the size of the IC. And we have been able to push in 12 millions of transistors, 12 billions of transistors, not millions, 12 billions of transistors inside that. So area is no more a concern if you go down to the lower technology. Power is a concern only for the portable devices and the critical devices, not everywhere. Again, speed is a concern only if you demand it for the specific application, not for every other application. Okay. And the next tenet I say is the fourth one is security. So, and now whenever you will do algorithm to architecture, the philosophy should go there that what is your application that you are targeting at. You said that yes, it is image processing, particularly if you say that police trying to control certain things over the. If I take this example, you appreciate and you will understand this one. Suppose somebody says that he's overspeeding. So overspeeding means you are taking your CCTVs are taking images and that is being sent over there. And that is one way. And then the speed sensors are there. And then you can identify which device is there. Now the question is that when you want to do it and what exactly you are trying to do it. Okay. See, there are possibilities like in USA, they say that the moment you overspeed, or in Europe, if the moment you overspeed, there is immediately a challenge that comes to your mail ID as well as mobile phone, a cell phone, saying that yes, you have overspeeded over here, the challenge is over here. Now, how does this challenge happens? Now, the question is that there are sensors which identify your CCTV captures you. You means your vehicle, and your vehicle makes an identification for you, and then it sends you. Now here, it is all that you are saying that yes, this is going. The moment it says that the sensor is there, then it sends an information. Then you have to say that you have to track that particular vehicle. After tracking the vehicle, whether you want to send it manually or you want to send it directly, that has to be done. So this particular stuff you have to handle it. Similarly, you say that the helmet. The helmet, of course, it has to be identified. No other extra sensor, but the sensor is the photography, the imaging part. So that way, if you look at it, you have to think that what exactly you are trying to do. Similarly, if you are taking a camera, a digital camera, which I'm taking about this one because your word that you have coined is algorithm to architecture. This word is used mostly by the DSP people. And then you have to select that, you have to capture this, but then a lot of other changes that happens. A lot of other changes means you want to do filtering, you want to do some more modifications, you want to do a lot of changes. Whether you want to do by that IC or you want to do it separately, that you have to capture, that you have to look at. So every time you come across a problem, always look at that what exactly is your target. Accordingly, fix the specs. And the requirements and specs, there are difference. And why I say there is a difference, the requirements are like specific, like dreams. This is what people would say that I want this, I want this, I want this. But everything cannot be possible. Can you imagine that somebody says that dishwasher हमने फेंक दिया और वहां से साफ होके आ गया? No, you just cannot do it. It's not possible. So if you say a dishwasher, then you have realized that you have to take it out and then put it inside. You have to add water. You have to do this. A lot of jobs you have to do. You cannot say that I just took my utensils, put it inside, and take it outside, and no time required. Somebody will say that okay, washing machine, I'll just go and put it. So that is why the requirements are always dreamy. Whereas specs which are given by engineers like me and you, are not dreaming. These are pragmatic stuffs. And when you do that, you have to say that what exactly you are looking for in the IC or SoC design. Once upon a time, we said IC design, but nowadays we are saying that a system on chip, because every time we are targeting a system and not a single chip. This, forget about this UPAM 741 or your flip-flop 7474 or JK flip-flop 7476. Those are there, but they are for specific things. But today, whatever we try to do is entirely systems. So looking at the target, I'll have to fix my stops and then accordingly move. And then I have to take a call whether I want to do ASIC design or an FPGA design. And then again, you have to take a call whether it is custom design or semi-custom design. And then proceed. And if it is semi-custom design, then again you have to decide whether you want to do a gate array based design or a standard cell based design. So everything is possible, but here what I tried to put into your mind that there is a new tenant, a new player, that is security, and this security has to be taken care of. And academics has become already concerned for the last 10-12 years. Not too old. Our team is one of the oldest team in the security, and industry is concerned even more, and now government is concerned. So when everybody is concerned, so let's have a look into that. So I would like to wind up at this stage, but I would love to have your questions. Seti sir, you can unmute the participants so that if there are specific questions, then I can answer.
Participant, if you have any question, please ask.
Yes, you are audible. Please go ahead.
Sir, which design that is better to design a processor, either FPGA or ASIC?
No, these are two different challenges. As FPGA or ASIC, see, at the end of the day, you have to finally design an ASIC if you are trying to come up with a product. Okay. But FPGA design is always faster to test something. That is why in most cases we do an FPGA based design. Okay. And but if you are thinking that you are coming up with a product, any product, say just say copy bending machine, that's the product, then it is always better to have an ASIC design.
Oh, okay, sir. Thank you, sir.
Hello,
Any
sir.
other question, please?
Yes. I'm able to hear. Please go ahead with your question.
Yes, sir. Sir, as we talk about this FPGA-based design,
Yeah.
we know that these FPGA chips are already like prefab provided by the vendors like Xilinx and Altera. So, are they also unsafe to use or put our design into those FPGA chips which are already designed and given by the vendors? They are already prefabricated, no, sir. So are they also unsafe from protection, from the security point of view?
See, they are unsafe because, see, you are trying to put your design into the FPGA. Okay. When you talk about the FPGA is already having its own lookup tables. It has its own mocks, multiplexers, and then it is doing this. That part is predefined. But what you are trying to do, that you are writing your own Verilog code or VHDL code. Okay. Now, if the Verilog code or VHDL code itself is defective, then imagine that these are some 10 figures are there which would have actually run your stuffs very well. But there is an 11th figure that is coming out, which is taking care of some mux and then putting it into this. In addition to your normal design, that extra part is creating an issue for your design. So that is never known because that's an IP you brought from someone else. That IP was not yours. Okay. And you can say that I tested my IP, but you have tested, but it has escaped from your eyes. So that is the problem, because see, that is only a mapping device. Even the security device, what I said about the POF, I said physical unclonable function. So I said that I will introduce a POP. That also I will introduce in the FPGA itself. So that will, see, if I go with an SRAM POP, then I will say that, okay, I am adding again that arbiter POP is having a mux and a lookup table. So this can be attacked. There is no way that, because it's in the IPs itself. People have attacked your IPs. But you will say that I don't trust that particular IP. I will test everything about the IP. The answer is yes, provided you can test everything from line 1 to line 1 million. That becomes sometimes very complex. Okay. So what we do is that whenever we take a third party IP, we believe that it is correct. Because it's already available. But the whole point is that whether it has been a correct IP, whether it is absolutely free of bug, nothing can happen, that nobody can get it. I hope you got the point, right?
Yes, sir. Yes, sir. Definitely, sir. Thank you, sir. So these third party IPs are like used with care, right? As far as I understand.
Yeah, they are used with care, absolute care. They are used with absolute care. But what happens is that, see, it is just like enemies. That is why I gave an example of, TI. I just told you so that you can easily figure out. I am an employee of TI today. I'm earning 10 lakhs. I'm not very happy. I say that 10 lakhs per month is not good. So I leave a company, I'll join somewhere else. I didn't join a company, I become a consultant. Okay. And tomorrow, then I know the everything that is available with TI. So I wrote down my codes, made some deliberate modifications and leave it over there. Then another engineer comes there, he tries to figure it out, or just before leaving the company, I made some modifications. He thinks that it is his company's own property and so wonderful things. He didn't try to check every line, every word over there. So that is sometimes not quite feasible. Not quite feasible in the sense that, as I said, it is because the number heavy. In analog design, there is no issues because the total number of transistors in an analog, if you look at op-amp, you can design it with 7, 8, 9 transistors. Comparator 20 transistors, PWM is 50, VCOs, PLL, and not more than 100 number of transistors. But here we are talking about millions of transistors. How do we handle each individual device? If I look at even if a digital wall also, see, I have my own eyes where I can, at a particular time, I can look at 50 elements or 100 elements. So more than that, it's becoming just beyond those things. So there are issues. So you can't, even if we try our best, and I have given some of the possible solutions, but new solutions have to come up and this has to mature, and this will probably take another 10 to 15 years. Okay, but the one thing for sure, there will be lots of jobs purely in hardware. There will be lots of purely in hardware means development of stops, because these stops will be developed along with the regular hardware and in addition to the security stops. Means the TVs that will come to the market maybe after a year or so, that will have security. So they will say that there are hardware engineers who are going to manufacture TVs, but in addition to that, they will add security to that. Every gadget, your telephone, your mobile phones, everything that you use. So the government is also spending a lot of money. So those who are teachers over here, please try to acquire projects from any of the government sources, including ISRO, DRDO, all the defense, BRNS, and all of them, and DST, MEIT, and all of them. So there will be a lot of projects on this hardware security and purely hardware development, because there is a new challenge now coming up. We use, yes, we all the time, whenever we are trying to use an IP, we check it, but this can always escape. So we will have to find out even more measures.
Thank you, sir.
So, good evening, sir.
Okay, good evening. Please go ahead.
Venerators, sir, present with my regards. I would like to ask, please, cite upon the modern day IC technology, neuromorphic photomix signal devices, and quantum IC device technology, and in terms of your security, complexity, and efficiency, to the conventional IC design that we have just mentioned over these slides.
See, the one thing is that I really don't work in that particular area, so it won't be fair on my part to make a comment at this stage, talking about those all kinds of design. But the security is a concern that is coming primarily because of the codes that we start writing. That is why I say that IP protection. So whether you are talking about the silicon or otherwise, or FinFETs, or even smaller devices or whatever that you will plan tomorrow. So this will also face similar situations. But there are changes, and that is why government is again saying that there will be more number of engineers which will be required, particularly for the fabrication. Hopefully, they are coming up with some fabrication plants in the country, where what kind of fabrication they will do is not clear at this particular point of time. But several meetings are happening. MEIT, the semiconductor research companies, and so on and so forth. So where they're planning that there will be some fab units will be coming. Whether quantum computing can come into picture or not, and all that, or carbon nanotubes will be useful. Those all questions will come little later. As of now, they are mostly concentrating and focusing onto silicon, and then beyond silicon now, FinFETs kinds of devices. Because we'll have to talk about those devices which are available in the market. Whichever device is not available in the market, it's not that we are not doing it, but that's only in the research. But if you talk about the security, we'll talk about those devices which are available in the market. So for that, we talk about silicon and FinFETs, not the other kinds of devices.
Thank you, sir. Thank you, sir.
I think there is no further question from the participant. So thank you, sir. It's a very good discussion, and also the presentation and nice way of representation. So you are discussing about the protecting electronic designs based on IP cores using ASICs and FPGA. Further also discussed the major difficulties of IoT in smart application. Thank you, sir. And also I thanks from our institute that you are accepting our invitation and giving a very good presentation for our participant. Thank you, sir. Thank you very much.
Okay, thank you very much for your kind words. I will send my PPT maybe tomorrow to Professor Mahanti and Professor Hota and Professor Sethi, whose mail ID I am having, so that
Yes,
you can. I have no objection in sharing it with the participants. Besides the recording part, you of course you share and upload it to the ASIC portal. You can share my PPTs as well. So I'll do that in a while. I'll send
Yes.
it.
Thank
And
you,
thank
sir.
you very much for asking me to come over here. And so I thought when everyone is going common, let me go a little uncommon and slightly different way. And because everybody is doing IC design and they only focus on power performance area, let me focus on something different. So my focus on security. So I tried. If the participants learned at least some percentage, I'm extremely happy, and they will take it up tomorrow. Thank you.
Thank you, sir. Thank you very much. So, dear participant, today the online week session, all the online week sessions this week, it is completed. So, I have already sent some articles, and kindly fill that annexure 5 and submit on 16th. Okay, the last day of our FDP. And further, I request all the participants that please come with your laptop on 12th at 9 a.m. because at the 9 a.m. the inauguration session will be start. Then after the inauguration session, we'll start our session. Okay. Thank you. Thank you very much.